So we've previously learned that if we have a molecule that has a chiral center being a location with unique stereochemistry, where there are 4 unique attachments that have a certain handedness associated with them, that we can go in and we can give an R or an S configuration. What we're going to do today is we're going to now compare 2 different molecules that are mostly the same, but the only difference is stereochemistry. And we are going to have 2 new terms that we're going to focus on. The first one we introduced already, an enantiomer, which is a non-superimposable mirror image, and then a diastereomer. Now let's go ahead and get back into the kind of thought process of our RNS configurations. So here we have an example of a chemical, and it has a chiral center associated with the wedge and dash where you see that alcohol. And there's an H that has a dash that's hidden. Let's go ahead and start by just getting an RNS configuration for this molecule. We're going to use our Kahn-Ingold pre-log rules. So I see that I have a oxygen, a hydrogen, a carbon, and a carbon as my first attachments. So my OH is going to have my highest priority, and my hydrogen is going to have the last. If I kind of do some comparisons between these 2 unique carbons, the carbon on the left, let's go ahead and start with, is going to be a carbon, and it is connected to a carbon, and a carbon. If I look at the right-handed carbon, that is a carbon that is connected to a nitrogen, and then a hydrogen, and a hydrogen. Make that bracket look a little less carbon-like. So in terms of comparison, my first is going to be a carbon versus a nitrogen. Nitrogen is going to win out. So overall, this is going to be group 2. This is going to be group 3. In terms of my handedness, 1 to 2 to 3. That is going clockwise, and my 4th group is in the back, so I'm done, and I'm going to give that a R configuration. Now, if we wanted to go through and determine its enantiomer, so if we wanted to draw its enantiomer, that's a word I probably am not going to be able to spell, enantiomer. So an enantiomer of this molecule is going to be a non-superimposable mirror image. And you can try to think about, if I had a mirror plane, how would I draw that and everything of that sort. But the nice thing is an enantiomer is going to be a molecule that has changed the RNS configurations to the exact opposite. So in short, the enantiomer to this molecule is just going to be the S version. And we can make the S version really easily by just changing our stereochemistry. So if I wanted to draw in the enantiomer of this molecule, I would draw everything the exact same. OH, OH, NH. So there's all my base. The only thing I'm going to do different is I'm going to change my stereochemistry. So I'm now going to have a wedge for my hydrogen and then a dash for my alcohol. The stereochemistry for this is now going to be an S because I've changed my wedges and dashes. You'll still have the same priority. Your oxygen will still be in 1, nitrogen 2, the benzene is going to be 3, but you're then going to rotate it or switch it because the 4th group is now in the front rather than the back. And these 2 molecules are going to be enantiomers of each other. And that's what we're going to be spending a bunch of time in this video. We're going to be comparing this kind of set of topics is we're going to be comparing multiple different molecules and then describing are they the same or are they different and what's their relationship. Now, if I had a molecule that had the exact same stuff where I had a wedge to the OH, it's the same molecule. There is no extra term. So if you have just a single stereocenter, it's either the same molecule and an enantiomer or a completely different molecule that is not a stereoisomer. So when you just have one stereocenter, that's a little bit easy. When you have multiple stereocenters, things get a little bit more complicated. And that's what we're going to spend the rest of this video focusing on. what happens when you have multiple stereocenters or multiple chiral centers? So in a scenario where you have exactly 2 stereocenters, there are 4 total possibilities that you can have for your stereocenters. And I've denoted these by these little kind of balls and sticks. The ball on the left is going to correspond to our very first stereocenter, and the ball on the right is going to correspond to our second. And for our sake, let's go ahead and just say blue equals R and red equals S. So in our very first scenario, we could have both of my stereocenters being R, and that would be an RR descriptor. I can also have an SS, an SR, and an RS. I'll maybe put like a comma between those. These are my 4 different possible combinations which I could have for my 2 stereocenters. And we've now built up the complexity, and we now won't just have the same molecule in enantiomers. We're going to introduce a new term. And our new term is going to be a diastereomer. And a diastereomer is going to be a molecule that is going to be a stereoisomer. However, it's not going to be a perfect mirror image. When you have an enantiomer, which is your non-superimposable mirror image, anything that was an R has to change to an S, anything that was an S has to change to an R. In a diastereomer, only some of the things are going to change. So if we think maybe of our original one of our RR, an enantiomer is going to be one where it's SS, where you have 2 unique ones that are different than the originals. Your diastereomers are only going to have some of them change. So if you were originally an RR, you might be an RS in your next state. So let's go ahead and kind of look at kind of what this looks like in terms of like actual molecules rather than some balls and sticks, even though we will come back to balls and sticks. So if we look, here are 2 different examples. The one on the right here are enantiomers, and an enantiomer is going to have a change in your configuration at every single location. So in each of these, I have the exact same backbone. So I have 1, 2, 3, 4, 5, 6. So that is a hexane. We think of naming. In terms of my numbering, I would do 1, 2, 3, 4, 5, 6. So this would be a 2, 3, 4 trichlorohexane. The position at 2, position at 3, and position at 4 all have the ability to go through and determine an R or S configuration. In a case of an enantiomer, every one of those needs to change. So if it was an R, it must change to an S in the other molecule that we're comparing to it. So here on the top one, we see that all of our wedges became dashes. So those 2 molecules, the one on the top and the one on the bottom, are going to be enantiomers. All of them have different stereochemistry. A diastereomer example is going to be one where you have some that change, but not all of them. So you'll notice the one that has the blue arrows associated with it. Maybe I'll go ahead and circle it here, and not blue at all. In blue was originally a wedge and stayed a wedge, where the other ones was originally a wedge and then changed to a dash. So only some of those changed. And those are going to be an example of a diastereomer. In many ways, you can think of a diastereomer as like a disaster. You wanted everything to change, but it didn't work out. Some things stayed the same, some things changed, and that's why we think like, oh, it's a disaster. That's not actually the root of the word diastereomer, but just the mental thing that I kind of normally think of to differentiate between an enantiomer and a diastereomer. To kind of show some specific examples here with a bunch of like balls and sticks, each of these are going to be 4 different examples. So we'll call it maybe A, B, C, and D. If we look at A, our original molecule has 2 blue configurations, and I think we called blue R. So originally, we said that this is an RR. An enantiomer of an RR must be an SS. Diastereomers are going to be random mixtures, so an SR or an RS, where one of them has changed but not the other. So for example, this one has changed but the other one has not. And those are going to be your examples of your diastereomers. And we have a bunch of different examples kind of shown with all the possibilities that you have there. You will only have one enantiomer. Depending on the amount of chiral centers, you can have a bunch of diastereomers. Let's go ahead and do one quick practice problem. We have a molecule here. It is a 5-membered ring, and it has a chlorine, and it has an alcohol off of it. Of those, we see that there are some wedges and dashes. Each of them have something that's not shown. On the chlorine, there's going to be a dashed hydrogen, and on the alcohol, there's going to be a wedged hydrogen. We can go through, actually, I'm going to do that in a different color to maybe make it easier, because it's going to get a little crowded. We can go through and we can determine our RNS for each of these. So let's go ahead and figure out our RNS. Let's go ahead and start with the chlorine. So the stereocenter by the chlorine, which is going to be this carbon here that we've just put a big dot on. For our rankings of my different groups, I'm going to have a carbon, a chlorine, a hydrogen, and a carbon. So that lets me do 2 of the rankings really easily. My hydrogen is going to be my 4th group, and my chlorine is going to be my 1st group. Of my 2 different carbons, my carbon on the left has a carbon, hydrogen, hydrogen. The carbon on the right is going to be connected to the alcohol. And the alcohol is going to be bigger than the carbon. So my number 2 is going to be over here, and then my number 3 is going to be over here. Maybe make that maybe over here. So when I'm trying to go through and determine my R and S, I'm going to start at my 1, go to 2 to 3. That is a clockwise rotation. And that clockwise rotation with the 4th in the back says that is going to be an R. So that chiral center that has the chlorine connected to it is going to be an R configuration. If I do the same thing with the alcohol, the 4th group and the 1st group are easily determined because I have an oxygen and a hydrogen. The other 2 is going to be a carbon that has just some carbon stuff and some hydrogens. The other one is going to be some carbon stuff with some chlorines. So my ranking from 1 to 2 to 3 is going to be moving counterclockwise. However, my 4th group is not in the back, it's in the front. So that is actually clockwise and therefore R. So that molecule, and we'll go ahead and redraw it because we've kind of got it a little more messy. So wedge to a chlorine, dash to an alcohol. We would call this RR. Now let's go ahead and draw in an enantiomer. And let's go ahead and draw in a diastereomer. So our enantiomer that we're going to draw in is going to need to change all of our chiral centers. So it was originally RR. We are now going to make it SS. And to make it SS, what we're going to do is we're going to change the stereochemistry at every single location. So I changed the chlorine from a wedge to a dash, and then the alcohol from a dash to a wedge. Now I have 2 different examples that I can draw for a diastereomer, and my diastereomers are going to be ones that are going to be RS as well as SR. So my RS, that's a horrible pentagon. My RS is going to keep the same R, so a wedge to a chlorine, and then I'm going to change my stereochemistry to make that into an S, which would be a wedge to my alcohol. And then the opposite, which would be my SR, is going to be a dash and then a dash. So for these, my original molecule was an RR. My enantiomer is going to be the SS version, where I change all of my wedges to dashes and all my dashes to wedges. And then my 2 diastereomers are going to be my RS and my SR, where some of them changed, but some of them didn't. So here, for example, my chlorine, let me do actually a different color. The things that changed, for example, here we showed the alcohol changing, here we showed the chlorine changing, but we didn't change the other one. Where in our enantiomer, we see that absolutely everything changes. And that will be one thing that you'll see in a decent amount of questions, where we will show a molecule and we're going to ask, what is the relationship between these? Are they the exact same molecule? Are they enantiomers? Are they diastereomers? Are they totally different molecules? The one other thing that we're going to introduce is going to be the word meso, and we'll go ahead and cover that really quick in a second. And understanding the relationship between those is really helpful. There is one special case where you can have a molecule that has chiral centers where you'd be able to go in and write out R's and S's, but overall it is not chiral. And that is going to occur when there is a plane of symmetry where your molecule is like there is a plane of symmetry, so there is a mirror image that exists like within that molecule. And these are going to be terms known as meso. So for example, in this case, we have two different molecules, both of which have alcohols. In the case where you have a wedge or a dash on your alcohols and they're the exact same, there is a mirror plane shown by the dash, and that mirror plane makes it so there is a mirror image. So that overall molecule is going to be achiral. And that description, I don't think I've actually written that word yet for you guys. Achiral is going to be a molecule that does not have overall net stereochemistry. You can still do an R or S at those individual locations, but there is no net stereochemistry. Overall, it is no net chirality, I should say. Overall, it is achiral. So of our kind of different ways in which we can kind of, if we're comparing two different molecules, they could be the exact same. They could be a constitutional isomer. They could be enantiomers. They could be diastereomers. Or you can have a material that's going to be achiral. Often they'll be meso. And then, of course, you have the option that they're totally different, where they're like not isomers. And these are the kind of 1, 2, 3, 4, 5, 6 different possibilities that you can have when you are thinking about your comparison between two different molecules. And the ones that we've kind of focused a lot are on the idea of your enantiomers and your diastereomers, which are kind of the two new terms. And we'll do a bunch of practice problems with thinking about those two, and there's also a bunch in your homework. We'll go ahead and end there, and that wraps up a lot of the talk on the relationship between two different molecules and the way in which we can kind of compare them.